Here's another combination of spring and masses. This is mass m1, this is mass m2, and with a string attached in between. Initially the spring was at its natural length and m2 was given a velocity v0 by impulse. Now the question is, what is the maximum elongation of the spring after this? Now we have to realize and analyze, when does the maximum length of the spring occur? Now as m2 goes forward, the spring gets extended, it starts pulling m2 backwards and it starts pulling m1 forward. Now, so what happens is that the velocity of m2 starts decreasing and the velocity of m1 starts increasing. So till the point of time when the velocity of m2 is greater than velocity of m1, till then the length of this distance between m1 and m2 will increase. Till the point where the relative velocity between m1 and m2 is not zero, till then the distance between m1 and m2 will increase and therefore the elongation in spring will increase. So the maximum elongation of the spring will occur at the point of time when the relative velocity between m1 and m2 becomes zero. That is, the velocity of m1 and m2 becomes equal. That is, the velocity of m2 reduces to some value v and the velocity of m1 increases to some value v. So till this moment of time the spring has undergone more extension. After this point of time, since the spring is in extension mode, it will pull m1 towards here and it will pull m2 towards here, due to which the velocity of m2 will decrease and the velocity of m1 will increase, due to which the distance between m1 and m2 will again begin to reduce. So this was the point of time when they both had a velocity v, that the spring had its maximum extension. So we know this point of time, so we apply momentum conservation from this initial position to this final position on the system in horizontal direction, because F external forces on the system is 0 in horizontal direction. So by applying momentum conservation we get m2 v0 is equal to m1 plus m2 into v. Therefore we get v is equal to m2 v0 upon m1 plus m2. Now we remember this result, v is equal to m2 v0 upon m1 plus m2. Why we did this was will become clear now. We can also apply energy conservation on the system from this position to this position, because the work done by external forces is 0, work done by internal non-conservative forces is again 0. Therefore we can apply mechanical energy conservation. Therefore potential energy initial plus kinetic energy initial is equal to potential energy final plus kinetic energy final. Initial potential energy was the spring potential energy, that was 0 because the spring was in its natural length, plus kinetic energy was half m2 v0 square is equal to half m1 plus m2 into v square, plus this is the kinetic energy, and we write the potential energy now, half k x square, where x is the extension in the spring, that is maximum extension in the spring which we want. We now know the value of v and we can feed it here. m2 v0 square upon 2 is equal to m1 plus m2 upon 2 into v square, that is m2 square v0 square upon m1 plus m2 whole square plus kx square by 2. So while we solve here, we get that kx square, we can cancel 2, 2, 2 and m1 plus m2 from here. We get kx square is equal to m2 v0 square minus m2 square v0 square upon m1 plus m2. So we solve this as kx square is equal to m2 square v0 square gets cancelled, m1 m2 v0 square upon m1 plus m2. So x is equal to m1 m2 upon m1 plus m2 into k root over into v naught. So this comes out to be the maximum elongation in the spring.